Hey YouTube, it's JP Dillon. Today we're looking at a mid-70s Pioneer SA-9500 Mark II integrated amplifier. This was sent in to me by a viewer of the channel. And the complaint is after a time the right channel just stops working. Regardless of input volume level, etc., the right channel just goes away. So we're going to try to figure out what the cause is, if we can get it to do it, service it, repair it, and do any other maintenance that may be needed. So, I got everything hooked up here. Let's flip the switch. There's the protect. Let's turn the speakers on. Alright, so right now, on the initial power up, as you can see, we have both channels. And if I switch the speakers on and off, that doesn't change. If I diddle with the tape monitor switches up, that could be a problem. Tap on that tape monitor switch and that right channel gets a little bit temperamental. Left one does too. And then we have input selector, which as we can see is rather touchy. We've got our mode switch, also very touchy. Muting switch, not great either. So he says this takes about an hour or so for it to really go into hard failure. And when it goes into hard failure, he can't get it back. So while I'm waiting for this to happen, I'm going to go do a couple of things, and then we'll come back to this machine in about an hour or so, and we'll see where it's at as far as it's misbehaving. And then try to troubleshoot it while it's in the failure mode. So, yeah, until then, I'm going to go do something else. Okay, so I've been running this thing for a couple of hours now. I shut it off briefly. Let's see if we're still at where we were before. And, oh yeah, hold on. I had to replug in the signal cable because I'd robbed it for something. But it's still not screwing up. So I called, sorry, I'm just moving stuff around here. I called the customer and explained what was going on. And so he was telling me that no, it's not just like a hard out. It'll get finicky. The right channel will come and go, and he can kind of mess with things like the volume control to get it to come and go. I noticed that if I played with the tape monitor switch, the right channel has a greater tendency to cut out, as we can see there. So yeah, it's time to open this thing to see if we can get it to, or coax it into failure. Because right now, it's happily playing away. So let's get the top open. Okay, so opened up. The first thing I notice is someone's recapped this machine. Now, why do I know that? Because everything here in the tone circuit is new. We've got new transistors, we've got new capacitors. A lot of work done here. Somebody's replaced a defective bias potentiometer. On this channel, there's some pre-drivers down there. Those TO126 guys are not original. So somebody's worked on this a lot. But the only thing I notice is that the four main electrolytics there and the regulated power supply are original. So, but not really that big a deal since there's no hum and there's not enough heat being generated adjacently. So we're going to tap on the input selector and see if that causes things to come and go. You see that the left channel flutters just the tiniest bit there when we tap on that. Just the tiniest bit. That could be important. Tap on the back of the volume control, preamp board. So far, no significant change. So let me peer down in here. I forget where the relay is in this thing. It's usually down here. Shed some light on it. Oh yeah, so there's the relay tucked in underneath the preamp board. So I'm going to set the camera up here. And we're going to poke at it. And I'm going to see if I can get it to mess up on that basis. Yeah, if I tap on that relay, nothing. Still rock solid. Okay, so that's okay. Let's peer down in here and see if any other work was done. Got some original caps there. I forget what that is. It's probably a regulator, or maybe the mic input section. If this has one, does this have one? No, it does not. So not a mic input section. Looks like a regulator for something. A couple of caps there that have been changed out. Let's look at see if there's any bad solder joints. Yeah, a couple of oxidized ones here and there. I could use a little attention. And then this is the cartridge selection. Someone's done a kind of a poor job of soldering that. Let's see here. How does the input selector attach? Yeah, bear with me. I'm trying to show you guys what's going on here, but it's not easy. Let me dip the camera down in here. Yeah, so that's just a single wafer back there. Input selector switch. So looking at the solder connections here, we have two rows. We got this row and we got this row. They're not great looking, but you know, wrapping on this thing didn't mess it up. I can tap on this thing, doesn't screw up. All right, so let's come over to the power amp board. Let's tap on some things on the power amp board. Absolutely no change. So far, I don't think it's a loose connection. It could be a bad solder joint that gets worse as it heats up. But like I said, I've been running this thing for a little over an hour, maybe an hour and a half now, and it ain't messed up. So we need to take a closer look at the signal path, particularly like the well, let's look at the input jacks here, since he tends to use auxiliary more than anything. These silly wire wraps. Let's poke the wire wraps here. No change there. It's pretty rock solid. Relay appears to be in good shape too, since I could tap on it and it yielded no change. Since it's been worked on, we look at the wire wraps and see if there's any oxidation or crust on them. Looking pretty good. Let's look at the other side. Left channel looks nice. I'm not too keen on that jumper, but it's not sloppily done. But yeah, this has lived a good life. No, it wasn't near the ocean or anything like that. So yeah, I don't know. It's a puzzler. It's one of those, it's not going to screw up when it's here. I mean, my only points of concern right now is down here we have a mode switch that's real touchy, that we can we could get it to screw up there. The tape switch particularly. Yeah, the tape switch has a tendency to make the right channel drop if I tap on it. So I'm thinking that's really our point of contention there. If there's an oxidized connection or a bad solder joint there, that would definitely tick things off. And he said it could show up in a recording too. Like he could take the record out and go to a tape machine, and the channel would be gone there too. So that's our point of contention, really. So let's get the bottom off, and let's see what the solder connections are like on that switch. Okay, so looking at the underside of this, there are definitely signs of previous work here. We had some soldering work done here. And we've had marks of capacitors replaced here, all up in there. Somebody took out the relay, probably to resurface the contacts. One thing I came across here, which is very interesting, are these markings. Somebody marked the wires and stuff. That looks like my handwriting. So I wonder if somehow I was the last person to work on this many years ago. But I don't think I don't think I did because I can't find the serial number in my database. Let's see here. Last 5 is 4293M. Let me look that up real quick. So it's been at 100% for like 10 frickin' minutes. This is why I hate Windows. Okay. So let's see here. 4293. Yeah, let's go. All yours. Just gonna think about it. Nothing found. Okay. Let's look up a 9500. Hold on. Yeah, so I can't find any going back to 2016. So either happened before 2016 or somebody has handwriting that looks like mine. Okay, so there are some oxidized connections, particularly back here. It's hard to see, but there's some ring around there by the number 10 and the one in front of it and stuff like that. And so if we kind of tap on this section of the board here and we watch the scope, yeah, rock solid. No point of sensitivity there. I mean, I will resolder this stuff so that it's happy, but yeah, I can't get it to screw up. And there is an oxidized connection down here on the volume control on the high side. Not sure what channel that's for, but that could be it. He says he has to mess with the volume control, so let's short out that side. Or no, that's our balance control. And that's for the left channel, not the right. The right's already been resoldered, so maybe that was like a point of contention previously. And then, let's see. Nothing wrong with the speaker selector switch. That's happy. So yeah, this is a puzzler. This is kind of one of those, it's not going to screw up for me. I will do some preventative maintenance. And let's see here, we've got stuff back here in this little regulated section that needs to be soldered there, like that section of the board. There's some crummy joints there, so we really need to go over this a little bit more in depth. I am going to resolder the tape monitor switches since the signal goes directly through them and there is some oxidation. Maybe along the lines of these wire wrap connections to the board too, because you can see some oxidation there at the base. Not very good looking. But yeah, and then we'll clean these switches. But other than that, I can't really find anything wrong with this. I think we'll do some services on it and then babysit it a little bit, you know. Sorry about that. So yeah, let's just let's work on the tape monitor switches first. Turn this off. Cut the zip tie to get that out of the way. Then we'll work on soldering up the connections on these switches, which don't look great. They're not terrible, but I'm trying to cover all the bases since this is one of those weird problems that hasn't reared its head yet other than just kind of playing with it. So we're going to resolder these because they do show some oxidation on the leads, and that oxidation could be up inside, which as the solder heats up could let go. So we're just going to resolder all these just to be on the safe side. And then we'll redo the connections the posts that solder to the board of the wire wraps. Absolutely boring, mundane work, but like I said, I want to cover all the bases. And it's weird how it looks like my handwriting's there. My handwriting's pretty unique. It's really kind of messy, sloppy. Somebody resoldered that point already. But let's just do it. And let me come down here. There's some ring around these. And it could also be that we're not in an environment where it gets warm enough. That's why I tried running it at about maybe 10 watts to get the amplifier warmed up, because maybe it's just 68 degrees in here isn't enough for the failure to occur. That could be temperature related. So I'm going to come underneath here and resolder these posts to the board. Because I've learned that Pioneer loves their wire wraps and they're not always properly secured to the board. Wire wraps are quick and easy, but not always the best at this day and age. Alright, so we got those resoldered. I missed this connection here. This looks kind of tarnished. And yes, I'm bumping the camera with my soldering iron cabling, so it's going to get shaky. And I hope the notifications get muted, because they're going off like crazy here. I keep getting one on my screen about every 10 seconds. Just blowing up. All right. So that takes care of the signal path there. We have our reverse switch. Just let me pan down a little bit here. This is the reverse switch, or mode switch, whatever you want to call it. Let's tuck this out of the way if I can. That should be resoldered, soldered, however you want to pronounce it. So let's go ahead and do that while we're in here. A couple of pins were resoldered previously. Definitely take care of all these ones that look oxidized. Okay, that looks a little better. And then let's focus on this part of the board back here where we saw those crappy connections. We got this dude here for sure. Let's try not to burn through the wire. Yeah, just basically trying to take care of everything that looks poor. And I believe this is a power supply for something, so I'm not... This has nothing to do with the right channel. Just something that needs attention. Okay, let's come up here and redo this one. And then there's one right here that doesn't look great, and the one next to it doesn't look great. Okay. Let's see, what else? There's a connection down here somewhere I noticed, next to the fuses. That's not great looking, but but that's for power again. It's this center one here we're going to touch up. Looks like a line for something coming right off of the fuses. Okay, and if we zoom out a little, we've got these ones here in the power supply, which don't look great. But again, this really has nothing to do with the signal path. These are just things I'm noticing. Okay, and let's check down here at our filter switches, which rarely get used, but if they get oxidized, they do carry the signal path, and they could present a problem. So this is preemptive. We're just going to do this because these look heavily oxidized, and I don't want them to throw off the trail here. And then there's the signal that comes down from the tone board. And let's resolder the feed throughs here, or the wire wrap post rather, over here. And then finally, ooh, that's interesting. Hold on. So this row down here, this is the speaker selector. Let me get this off the mount. You can see this better. That there, that looks like a dry joint. Come on, focus. Yeah. So that up there, that very top one there, that's for sure a dry joint. And then just looking around here, all these kind of look cruddy. So yeah, let's resolder that. Let me just stick this back on the camera mount. Definitely want to take care of that. Problem is, I don't think this goes anywhere. I think this is just a placeholder. There's no traces attached to it. So that's probably not it either, although all of these connections are kind of oxidized and should get changed. That would definitely piss off the connectivity to the speakers. Okay. That looks better now. Okay. So now that we've taken care of that mess, I think the next thing we're going to do is see about cleaning the pots and switches. So back there, where the holes are, those are your tape monitor switches. And let me get some contact cleaner back in here, and we'll work these. Let me adjust my nozzle. Can't really see it, but there's that. Let's do the other one. And we'll just work them a bunch. Get all the cleaner up in there. I'm wondering if I should resolder the input selector too. Probably. That'd be a good idea. Okay, and then to clean the input selector, this is going to be hard to show, but the wafers are down there. See that? So you need to get the contact cleaner down into those wafers. So this puts a little there, a little there, a little there, and then some from the back side, but and then we'll work that. And then the phono selector switch is that guy back there with the open back. So that's a little fun to try to get to. Okay, so then we'll work that. Zoom out here so we're not just looking at a blank circuit board. That's your phono cartridge load selector. Actually, it's load capacitance. The other one's the load selector. And that's the one down here, which is much more easy to get at. So we're just going to get a little contact cleaner in there and work that one. And then the mode selector, which is that big white thing down there. You got to get it in between where I'm spraying there and that edge, because the switch contacts are behind that. And rotate that, clean it up. Okay, and then there's the muting and loudness switches, which are these guys. Yeah, we'll just work them a bunch. Okay, and the balance control, there's a little hole on this part of the pot, and then you can get the other bit of it in there. All right, I don't know where. Use some CRC on the volume controls, because the volume controls are somewhat fragile on these, and you don't want to hose them with D5. Hang on, let me attach the straw here. Yeah, we're just going to get it inside of here. And then work this guy. And then you can see that pot's loose there, so we need to tighten that down. We need to tighten the knob too. Okay. Let's do the tone controls. Tough doing this one-handed, so bear with me. And you have to be quick, because this is quick drying. Yep, somebody's already done the recap on the tone board. He'll be happy about that. He was wondering about that. Come on. I know this is just so exciting. I'm kind of upset that I can't get this thing to go into hard failure, but if it's not gonna, it's not gonna. And then the tone switch, I trickle it down in here on the side where it's exposed. rather than through the top. It tends to work better this way. As you can see, switch moving back and forth there. Let's see, we already got our filters and stuff, pretty sure. Or maybe I didn't. Oh yeah, filter switches are way down in here, which may be difficult to see because of the cabling in the way. But yeah, I'm just gonna clean them and then work them. And then finally, let me set the camera down a minute. You got our speaker selector thing, which is right up in there. And hard to see on camera, but I'm getting the cleaner down between the gap like the mode selector. Okay. I'll work it more if it needs it. Let's resolder the input selector switch real quick, and then we'll turn it on and see if any change, though I doubt it. Okay, so there's our input selector. Move this out of the way a little bit. It's going to be tough getting around this stuff, but I think I can manage it. Let's get this wire out of the way. That definitely looks cruddy right there. That's definitely about ready to break free. So let's go ahead and resolder the input selector. Move this out of the way. Oh yeah. Now that you uncover the wires here, you see a lot more oxidized connections on this, which, like I said, when it heats up, could let go and cause the problem. Okay, there's that. I'm just kind of looking around on this input board. See if any other things kind of stand out for me. I'm just going to touch them up. That's got a little ring around it. Somebody's resoldered this switch already. This has got a ring around it down here. Basically anything that looks questionable, I'm just going to resolder at this point. Somebody's jumpered that. And we got this up here, which looks kind of shoddy. That looks okay there. Not thrilled about that. Okay. All right, time to turn this thing back on and see if there's any points of sensitivity now. Looks pretty good. Definitely don't have that sensitivity or touchiness anymore. Muting switch works wonderfully. What do our tone controls look like? Yep, pretty smooth, no DC. That's what I'd expect from a recapped machine. If you see the waveform is bobbling around, then you got some DC there. No pops from the filters. Speaker switch latches wonderfully. Balance control smooth. So, yeah. Let's check phono here. Let me switch the cables real quick. All right, so we're on phono now. Load switch is clean and noise free. Let's check our compensation. Yep, curve's working pretty good. All right, so this thing's pretty happy. No sensitivity from that switch anymore at all, or the input selector for that matter. Everything works like a Swiss watch, just perfect. And then if we let me see if I can zoom in here on the scope and overlay the channels. It's a perfect overlay. There's no phase shift, so that's good. It tells me that things are working as they should. So I think this thing's good to go. I'm going to run it for a little while longer. And then the last thing we'll do is take the front panel apart and we'll tighten down the volume control and the knobs and all that stuff. And then this thing will be ready to go. But, yeah. Haven't gotten it to screw up yet. And it's looking real nice now. So we'll see what happens. Okay, so let's take care of the last thing, which is the loose volume control knob. And the way that you get at that, somebody's glued this on. That's nice. We'll fix that in a moment. Same with that one. The volume knob has a hex key on it, which I believe is 1.5 millimeters. Could be a 2, but I think it's 1.5. All the rest of the knobs and toggle covers just pull off. And I put the cover on for testing to heat it up a bit. So we're going to remove that. I already had it unscrewed. And let's see if it's the 1.5 or if it's the 2. Let's try the 1.5. Let's just see if that catches. I don't feel anything in that hole. There we go. That's loose. I don't feel anything inside of this one, so maybe focusing on loosening this up. Let's see if the keeper's actually in there. Yep, that one's in there. I can see the little screw pushing down, but that one's missing. You can tell because my tool goes in there. And I don't have another one of those hex keys, so that's why the volume control gets loose. But let's finish removing the rest of the face here. Pull all the toggle buttons off. And then we'll loosen the nuts on the front panel here. And then once we get the front panel off, there's a keeper screw up top, right in the middle here. Once we get this off, Then there's a plate here, which is just stuck on there with double-sided stick. So be careful when you get it off of here. Somebody's already made a chooch mark on it. We're just going to pry real gentle. Work it around the edge here. And once we get it loose, then we can get to the nut behind it, which is that guy right there. And so we're going to tighten this. Somebody put Loctite on it before, which obviously didn't work very well. So we're just going to tighten that up. Now I can't rock the volume control anymore. We're going to put this back, press it on, and while we're at it, we'll check the couple of others. I can remember where I set it down. There we go. Just make sure all the rest of these are snug. That was a little loose. Okay, so we'll go ahead and put the faceplate back on. We'll put the keeper screws back in place. And of course, I drop it on the floor. Okay, those are all hand tight. Let's tighten them down. And once you got those in there, then go ahead and reattach the little keeper screw. And so the next thing I'll do is we'll index the volume control. Since we're at the infinity portion. We'll tighten this down as good as we can get it without stripping it. It's got good travel. And we'll start putting the other knobs back on. Make sure they're indexed properly. And we have to address the couple that came apart. Okay. Now when they separate, what I'll do is I'll get the tiniest little bit of tacky glue. You can use tacky glue, you can use speaker glue, but basically it has to hold the knob on there, so I'm going to use my infamous black goo. And I'm going to put just a little dollop inside. You can see it's keyed there. And then we're going to match the key, which you can see there. We're going to match the key up with the indent inside and just push it down in there. And then we'll put the knob on, and you can check by wiggling it as you put it on to make sure it's not off key. And repeat the process. So again, dollop of glue on the inside. Make sure we got the key right. And then we'll match the key up and just push till it locks in. Wiggle it as we put it back on to make sure it's in place. And there we go. And obviously all the toggles we just push back on. Helps to keep them in the right orientation. All right. And then after this, we'll let it warm up a little while and we'll set the bias and offset. Although I think on this one, the bias is the only thing adjustable. I think the offset's determined by the differential pairs. Well, I could be wrong about that. But when in doubt, consult the service manual. I just don't see any adjustments for it. I think it's based on a fixed match set of transistors. Okay, so anyways, let's go ahead and hook it up, turn it on, and let it warm up a little while, and then we'll set the bias and then get it dialed in. So there it goes, click. And let's just check the offset real quick. So we've got on speakers A in the left channel. We have point, it's probably close to 0 as you can get here. It's about 0. And if we go to the other channel, we can see that it's a whopping 5 millivolts. And there is no adjustment on this amplifier. It's entirely based on the matched pair, which is a dual transistor device. So yeah, 5.7 millivolts and 0 in the other channel is pretty excellent. And down there, that's your little differential amplifier pair. And that pot there is for your bias, but there's no other adjustments, and the service manual confirms that, so it's just the bias. So let's consult our service manual and see what our bias adjustment is. Okay, so it looks like between pin 3 and 9, 30 millivolts, and then between 6 and 12, 30 millivolts. I guess they're just asking you to check for both pairs, because otherwise it doesn't really care. It's going to the same emitter junction. And I have shorting plugs in the input to the power amp. Yeah, there's no offset adjustment, it's just bias only. Okay, so between 3 and 9 we've got 27.3, and that's after a warm-up. That's just the tiniest little bit low. These really should have been multi-turn pots, but there we go, 30. And let me switch the leads to 6 and 12. And it varies 27.6. It's, however, the second set it does say 30 millivolts plus or minus 10 millivolts, so that's still within spec. So let's do the right side. And you can see the right side's a little low. We're going to very carefully adjust this and hope it doesn't blow up. One mistake on tweaking the bias and it goes kaboom. So there's our 30 millivolts. Let me switch the leads. Okay, so we have a problem. And so when we switch the leads, we see that no current draw is occurring. So that means either A, one of these devices is open, or B, we've got an open connection somewhere. So we need to troubleshoot that and figure out why one set of output transistors is not conducting. And I double checked, and we are hooked up to the right places. The 3 and 9 measurement we took was fine, but the 6 and 12 measurement we took is not. So we need to better investigate that and tear it apart, figure out where the break is, because that means that one set of output transistors is not fully conducting. And that would mean premature failure, and that could also mean why he's not getting full output on the right channel, or it intermittently goes away. So let's investigate that. Okay, so let's take a look at this. And basically what they have here is they have two sets of transistors that aren't quite in parallel, but they are connected with some emitter resistors between them. So the first set we measured, which was between 3 and 9, we got current. So that tells you that Q1 and Q4 are conducting and they're happy. But when we measured between 6 and 12, which is between Q2 and Q3, we weren't getting any current flow. Now, it's unlikely that the stage prior to that is at fault because it provides drive to all 4 transistors. So what we could have, and again, it's not very likely that it's going to have the R20 or R21 open, because again, that feeds both sets, and we have one set conducting and we have one set that's not. So the next thing we have to look at is we have to look at these small resistors like R25 and R24, but again, that probably would not affect current draw, although if they were open, that would screw up the biasing circuit. We look at R18, which would be the emitter resistor for Q2, or R19, which would be the emitter resistor for Q4. Actually, no, we don't need to look at that one because Q4 was conducting. Instead, we would look at R17 and R18. So those are the two emitter resistors. If either one of those is open, that would stop conduction. Now we also have to look at the probability that Q2 or Q3 is open. And if either one has like an open base emitter junction or something like that, then that would stop it from conducting too. So there's all this stuff that we need to check. And it could just be something simple like a broken wire, since somebody obviously had these boards up and was working on them before, whether it be me or someone else, I don't know. But it's all stuff we need to look at. And it's all very important that those items be checked because there's obviously an interruption in the signal path. The bases are tied together. The emitters are tied together in parallel, so it's either likely open emitter or open transistor. But gotta check it. Okay, so the first thing we need to do is we need to identify whether any of these emitter resistors are open. And so this is the pair here, this transistor here and this one here, that we're not getting any current through. So we need to ohm out these resistors here, and we need to see if they are open, because if so, that would stop the current flow and that would prevent us from getting our proper reading. Now, as you remember, we were getting like, instead of 30 millivolts, we were getting like 0.08 millivolts or something like that. So it was a very minute amount of current flowing. So we're going to check this, and we're going to see if the emitter resistors are open. Now, if they are, obviously we replace one and we recheck the circuit again. If they're not open, then we have to check the output transistors themselves. We may have an open output transistor, base emitter junction, or otherwise. We'll also check these fusible 100 ohm resistors, although even if they are open, I'm not sure that that would kill the circuit. You'd probably get distortion and such, which we did not see on the oscilloscope, although we weren't cranking it, and I don't want to crank it if it's not properly distributing current, because that will just kill the working output transistor. So let's take some measurements. Now this is going to be a little awkward because of where I'm positioned and where everything is. So if I block the camera momentarily, I apologize, but that's just how it's going to be. So the first thing I want to do is try to measure these emitter resistors. And this one down here is probably the most difficult to get to, of course, without taking the entire board up. And it may be that I have to take the entire board up. There we go, that's a little better. There we go. Alright, that one's alive. And although they're 0.5 ohms, you're going to get some resistance through the leads. That's just how it is. So this would be one of the emitters in that circuit that we could not get a reading from. That emitter resistor is alive. And so another quick way to check is to go between the emitters of the pairs, which are tied together. And so we are reading across both resistors. So those are okay. Let's go to the next set. We got that one there. And we got that one there. And if we come to both emitters, we're getting current through both emitter resistors. Okay, so the next thing let's do is just take some measurements from these 100 ohm fusibles here. If I can get my meter probes in there respectively. Let me see if I can shift the insulation back enough to get a probe in there. It's like a big if today. See, I should be getting something. May have to get my little needle probes. Nothing, huh? Let's just make sure I am not improperly connecting this. 51 ohms there. Yeah, there's two hundreds in parallel, so that would make sense. So that is probably okay. Let's see if I can shift this one down and take a measurement on it, or if it's going to fight me. I'm thinking it's going to fight me. I'm going to try to move back a little bit of insulation here without decimating the resistor. Okay, let's attach there. And then let's see if touching this. Okay, so both of those 100 ohm pairs in parallel are present because they measure 50 ohms for the pair. Okay, so now we're running into a conundrum because the emitter resistors aren't open and the protection resistors aren't open, but we still didn't have any current between this pair and this pair. And they're supposed to be paralleled. So that tells us that there's a good probability that one of these devices is open. Now, if I just do a quick diode check, that probably won't reveal anything useful, because usually the diode check does not reveal a full open. gotta switch polarity because I think this is the NPN or PNP side. Yeah, see, diode check, we look okay. So the next thing we're gonna do, plug it in, turn it on, take our measurements again. Hope and pray that it was just me with a bad test lead, although that doesn't seem very likely. It's not impossible. And we're going to take some measurements across the devices itself. Now, it could also be that there is a bad socket housing one of the transistors. So let's see here. Let's go back to our working pair. So 3 and 9. We got a reading there. It's warming up, so it's going to start low. But there, we got nothing. Okay, so let's check the voltage across the base emitter junction of that set. So here's the NPN. I'm going to have to switch ranges here. We've got 0.5 of a volt across it. That's about normal. Let's go to the PNP here. A little bit higher, 0.6 of a volt. Let's compare that to the other working channel, just for grins and giggles. Let's see, so we needed 3 and 9. Or was it? No, it's 3 and 9. So 3 and 9. I'm getting 20 mils there. 6 and 12, 19 there. And if we measure across the base emitter junctions, we get 569, 569, 576, and 578. So the ones with the higher base emitter drop are drawing less current. They have more, well actually, no, 0.6 of a volt. The ones with the higher drop across them are drawing less current, because usually when you have a higher bias current, it does pull it down a little bit. So the fact that I have one transistor here with a much higher current than the rest of them, and this was one of the ones that I was not getting current rating through. So just for grins and giggles, since these are paralleled and these are paralleled, let's see if we get identical readings here. So if we go to 3 and 12, we get 12 millivolts there. Supposed to be getting about 30. So get 3 and 9, 24. So if we do 6 and 9, we get 12, and we get nothing there. Interesting. So definitely someone's not conducting. And my money's going to be on this guy with the really high voltage drop across the base emitter junction. So let's reorient the machine and take a measurement from the transistor body itself. Now obviously I'm not going to be able to get to this one down here, but if we just do a process of elimination, we can figure out who's who. So that's 562 right there. So the other one, which is down below, is the one we were getting the higher voltage drop across. Usually when you see in parallels, the one has the higher voltage drop because it's not pulling any current, it's not conducting. So my thought is this 2SB618 down here is an issue. First I need to see if I have a substitute or a direct replacement, and then we can swap it out and see if that changes anything. And then if not, then if I don't have a substitute, or a direct replacement rather. I need to come up with one that's electrically equivalent that will work in its place. These frickin' batwing transistors are not easy to get. But hopefully it's just the fact that this one guy down here is no longer conducting well, and that's why we're getting the bias anomaly, because he's not doing his job. So let's see what I have. Okay, well there is the little bugger pulled out. We can do the diode check briefly again, but like I said, the diode check really doesn't show the true condition of the transistor. And again, trying to do this one-handed, so bear with me. Alright, I'm going to set the camera down for a second. So our base emitter junction looks about normal, 0.506. And then if I slip down here, 0.499. So from the standpoint of junctions, that's okay. Let's stick it on a component checker and see what the rough beta is. Yeah, and this says it has a beta of 88, which seems a little high for this device, but yeah, okay. And this device says it's 102 beta, and the turn-on voltage there, 624. It's a little high, isn't it? Here's the other one out of the same socket here. Yeah, 641. Beta on that one significantly lower. So, yeah. Hard to tell which one's not right and which one is. They both test vastly different gains, although you can't really tell the true gain of a device with one of these things because it's not putting enough load and current through it to really ascertain. I mean, we can do repeat tests. Yeah, it's still high turn-on voltage, but let's see here. Yeah, going back to the other one, you still got this super high beta. It's a difference of 20, so that's obviously current hogging, and that may be why we're not getting proper load distribution here, so they really should be matched. Problem is finding another set of these 2SB 618As. I believe these are 30 megahertz, 80 watt. Yeah, let's look it up real quick. Yeah, so it's 150 volt, 7 amp, 80 watt at 15 megahertz. Let's see what the collector capacitance output. Yeah, that looks like that's going to be 340. There are people saying you can use the FJP 5200 and FJL. Actually, no, it's whatever the counterpart is to that. It's a wider bandwidth. The output capacitance probably isn't really what I'd like it to be, but this is supposedly a usable sub. And it's a TO220 instead of the batwing, so I would have to drill an extra hole. Not really keen on that. Audio Karma's got a bunch of blabber about that. Yeah. So, and Semitronics has the original, but they're $13 a piece, which is, you have to weigh against a couple of items. Number one, is it a legit part? It looks like it is. There'd be not a lot of point in making counterfeits. But then you don't know what the gains are. So then you got to buy a couple so that, you know, you get the gains right. Because right now, the issue I think is that one transistor's got a gain of 100 and the other one's got a gain of 70. So one's hogging all the current and the other one's not. So the load distribution is not correct, and that's why we're not getting proper bias, because one's conducting more than the other. So we really need more of a matched pair in there. Well, if you use something else, like the MJL things, obviously these are overkill. They're huge, and there's no stock of them. So you got to wait for that. And then you got to take the time to modify it, wire it up, and all that sort of nonsense. Same thing with the Fairchild device. Yeah, it may work, but then you got to mess with it. And you got to drill holes in the heatsink and provide extra isolation, and then still get the original sockets to mount unless you want to put new sockets in and wire it up. So, yeah, I'm thinking I'm just going to bite the bullet and buy a couple of these 2SB618s and hope that I get close enough betas that it'll work in the circuit. And go figure, I got some 2SD588s left. And you can see I wrote the beta on this one. But yeah, look at the date that was originally acquired, 87. And I did not buy them when they were acquired. I was a little tight when they were acquired. So this is old inventory that we acquired from another shop. And we have these, but I can't find the PNP counterfeit or counterpoints. Blech. Try again. The PNP, bleh. Ugh, the counterparts. There we go. So basically, we need to get a matching set in here, and that should fix the problem. But for now, we just gotta wait until we get those parts, and then we can work on getting this thing dialed in, because what's going to happen is if you just ignore that, you're going to create two problems. You're going to have current hogging, where one device with the hotter beta is going to take all the amplification, or actually the one with the hotter beta is going to work less because, you know, more out from what comes in, and the one with the lower beta is going to have to work harder. But, or am I getting that wrong? Yeah, this has been a bad morning with no coffee kind of day. So, yeah, I'm going to grub around a little bit more and see if I can find a dead board or something with those devices in it. And if not, then we just got to wait. Now, I do have some 2SB616s, but they're not as beefy. Can't really use these as a substitute because they're only good for 60 watts instead of 80. But as you can see there, well, that's the counterpart, the 2SD586. So yeah, I screwed that one up. They're even mislabeled. I think that's just written in there for the sheer sake of that. So that's the NPN, so that's not going to work either. I was thinking, hey, I'll pop these things in and see if the bias problem goes away, because idling ain't going to kill it. But I misread it. It's actually these. These were filed in the wrong place. So let me put these back. Alright, so yeah, looking around, poking through everything, I don't have any others. So we're just going to have to wait until these get here. And then we'll pop them in and see if that fixes it. Because I wouldn't want to let this out of here with one transistor being a current hog, because that would probably mean it's failure, and then, you know, things would come back, and I don't want that. So I'll get with him, talk to him, say, hey, it's going to be a little bit, but yeah. So that's where we're at right now. Just got to wait for him to get here. So fast forward a couple weeks, and we got this set here. I bought this from Consolidated Electronics. He says they are close to match as they can get. He had ones in the 40s, in the 50s, and in the 60s. So I said, well, I'll take a match set in the 60s if you got it. So he sent these to me. And they look legit. They look like the real things. So we'll just put them on the beta checker real quick just to be sure. And then we'll pop these guys in. Okay. So let's do number 1 here. 57, 58. And what are you? You're 63. That's not very matched, but you can't really tell without a curve tracer. Let's see. I've got a third one here. Let's check that one too. Okay, well, here's the third one. See, that one's 53, 54. 54, 58. And this one keeps changing. It's like 64, 65, 66. So the ones that we yanked out of here, I remember one was like stupid high. Hang on. Let me take my hand and open the bag. Get the old parts out. think I marked these too. Like one of these was stupid high. This was like in the hundreds, which is like not okay. So that's 65. Yeah, like 87. That seems high for that device. 57. And it changes. So this is not the most reliable thing. So here's a 60. What was this one, like 62 or something? This one's creeping up to 70. So there may be something illegit about this tester. Let's get the other one. Okay, well here's the first one that I have marked at like 100 something. Yeah, so that reads 102. Let's do the next one. Here's the next one. I measured 70 something. Yep, that's 73. Okay, on to the next one. Here's one of the new ones. 64. Here's the next one. 55. Here's the last one. 59. All right, well, yeah. 59, 55, that'll work. 59 and 65, no matter what they're for apart. So, yeah, that's what we got to work with. So, his results and my results may differ because, A, he may have used a curve tracer, which is a more accurate way of determining betas. I'm just using crappy little component testers. So, a beta of 4 difference really isn't going to matter a whole lot on these things. 55 to 59 ain't going to matter as much as 70 to 100. Beta of 30 difference is going to matter more than a beta of 4. So let's get these things prepped and pop them in. Alright, so let's clean off the old heatsink goo. It's not dried and crusty on there, which is good. That says that it hasn't overheated or been subject to abuse. That means that I can probably leave these alone since they're not going to be crusty. And I'm going to take a shop towel and just rub off the old heatsink compound from the micro wafers. You want to be careful not to damage these because they really are hard to find. Just going to get off as much as we can so that there's a good clean surface. I'm just pinching and lightly pulling because you don't want to break these. So let's go with the next one. These have to make good thermal contact, otherwise how are you going to get your heat away from your output transistors to the heatsink? Also, we're going to need a little bit of trickery because these sockets are not mounted to the heatsink. They rely on the transistor to hold them to the heatsink. So I'm going to have to put some pressure behind them with a tool or something while I get these installed. Okay, so I'm going to take a look at the old one. And we can see that we have a 90-degree bend about halfway through the thick portions of the leads. So I'm going to take my, bashing the camera here, I'm going to take my small needle nose and make a bend about at the same place here. That should work. I'm just going to hold it up here briefly and see if that all lines up, which it does. Okay. So the next thing we do is apply the heat transfer compound, and you can get one of these little MG Chemical 860s. This little jar of thermal paste will last you a long time. So let me crack it open. And so I'm just going to stick the busted end of a Q-tip in here. Put a little tiny bit on the end. You don't need much. And then I'm going to apply it with the Q-tip. The nice thing about this is it provides a nice flat surface for transfer, so it's easy to transfer. Don't get this stuff on your clothes either. It's hard to get out. And then with that coating on there, I'm going to rest the mica wafer on the transistor body like this. Apply light pressure so that it doesn't have a tendency to slide around or move. And then we're going to do the same thing again. And we're just going to apply it very carefully to the mica wafer. You just need enough to cover it. You don't need to slather it on. So now what I'm going to do is I'm going to get a tool. Could be anything, could be insulated, non-insulated, doesn't matter. You should have discharged your power supply anyways. So I'm going to take the butt of this pin and I'm going to put it behind here and push against the back of the socket, and then carefully work this in to the socket. I'm not going to push it in all the way yet because I need to get the hardware seated and properly threaded. And we'll very carefully rotate it counterclockwise until we feel the threads catch. Don't tighten it down yet, just get it so that it's touching the heatsink. Again with this. And we're just going to finger snug it. Do the same with this one. When you see the stuff start to ooze out of the sides, then you can tighten it down a little bit at a time. You don't want to tighten it down super tight, just snug it. And there's one. You also don't have to worry about clipping off the center leads. Even though it doesn't use them as a conductor, you can use them as a guide. You might be able to see here, there's no metal conductor on the center collector lead, but it does help get it in there safely. The one down here we're going to have to fidget with because it's broken loose. But anyway, let's get the this one prepped. So we can get it in there. Almost. Of course, this one's going to bend a little bit. All right. Now we'll get our heat transfer compound on there. Then we'll very carefully put our mica wafer on here. And just apply light pressure and you'll see the heat transfer compound distribute. You can see this mica wafer is a little bit warped. As long as there's no cracks in it, that's what's important. Then I'll reapply here more thermal goo on the outside. Okay, now here's the fun part, because we have to wrestle the socket back into place. So I'm going to set the transistor down, hopefully not drop it, because my hands are full of nasty heat transfer goo right now. let's see if I'm going to grab the socket with my needle nose and try to work it into place here, if I can do that. Okay. Now we'll take the butt of our pen again, smacking the camera mount. And we'll come down here from the top, and I'll see if I can push on this as I insert the transistor from the front. And I'm at somewhat of a disadvantage because there's less leverage in my favor given the distance between the fulcrum and the transistor socket. So we'll see. I'm just going to have to get in the way here a little bit. Again, now we're going to run into an issue because the mica wafer came off of the transistor. So I'm going to use a pick as a guide to shove it back up in here, which may or may not work for me. Alright, so while that's holding that there, I'm going to take my first screw and try to guide it into the hole here, which is probably, yep, going to make the tool fall out and make the transistor come out. This is the fun part. And make the socket come out too. Man, that's like a triple score. Alright, we got to try again. This is the fun part that I don't normally show because, you know, requires effort. And I'm on a bit of a tether because they don't provide any means to unplug this. So I'm going to try a different tool. I'm going to try a hook tool and see if I can get the socket up in here a little bit better. I'm going to hold it with the hook tool, and then we're going to use my previous tool to guide the mica wafer. Give it a little press on here and hope that the heat transfer compound holds it there. Then we're going to attempt to reinsert the transistor. Then put a guiding screw in. Then put another guiding screw in. And bash the camera again. Then we'll get the threads to catch. Yep. This is the fun part. Guiding the socket into the heatsink, so that's good. And I can snug these down. Okay. So it's in there. All right. I'm going to get one piece of hardware to hold the heatsink in place. And then we'll fire it up on a dim bulb tester, because you should always start an amplifier with a dim bulb tester after you've worked on it. I don't care how good you think you are, you will fuck it up. There have been times where I've done that, where I thought everything was cool, and there was one little tiny thing that I had missed that when I powered on, shorted out against the chassis, and there went my afternoon. So just remember to do that. Okay, so let's get it hooked up. Okay, let's flip the switch. That's a good sign. Comes right up. Okay, so let's take it off a dim bulb tester and then let the set warm up. And we'll check our bias and stuff and see if putting the closer matched transistors in there yields us the adjustments we need. Okay, so after this has had an opportunity to stabilize, so we've got our 3 and 9 hooked up, and we've got 29 milliamperes holding steady. So let me hook up 6 and 12 and see what we get. And 6 and 12 yields 24. A lot closer. So now that we have a more matched set of transistors, it's behaving correctly. Now, according to the service manual, the second set, 6 and 12, can be within plus or minus 10 of the original value that you got from 3 and 6. So this is a happy machine now. And so we're going to burn it in a little bit longer and see what else it needs, but I think this one's ready. Okay, so it's never not fun here. I've been running this thing for a while, and all of a sudden I noticed that I kind of smelled something hot. And this channel that we just worked on was getting stupid hot. Pulling out the infrared thermometer, this transistor here, the case of it was just crazy. So I yanked it, and it tested super leaky. So I found one close to the bottom, which was beta 48. And this one was, I think, 52 or something like that. So again, 4 off. Rebiased it. It's stable. It's been running now for about an hour and a half, and it's still happy. And one thing that I think has been cured that I noticed before was asymmetrical clipping on the right side, which is not true anymore. Now both channels clip absolutely symmetrically, which is great. So, yeah, out of curiosity, let's see how much. Let's see how much balls this thing has. I'm just going to hook my load up to my meter. Or actually, hook the meter across the load is the appropriate term. And let's crank it. So that's 27 on the right channel. And let me move it over to the left. It's like a 1/10 of a volt difference. You'd never hear it. Okay, let's do the math. 27 squared divided by the resistive load. So that comes up to 91 watts per channel with both channels driven. Not too shabby. And it's been running at full tilt now for about an hour. And those heat sinks are hot enough to burn your skin. They're about maybe 68 degrees centigrade, which is pretty toasty, but it's doing it. So yeah, I think this one's ready to box up. Very nice amp. All the weird little quirks we worked out appear to have made it happy. So anyways, hope you guys enjoyed this one. I know I don't do a lot of audio stuff these days, but this one was kind of a cool project. And you got to see it all together. And you got to see the importance of beta matching on the outputs and how it affects the drive and the output and all that stuff. So anyways, thanks for watching. More stuff to come.